All right, let's get this party started. We got section 8.4, natural logarithms, or as the French would say, logarithms naturels, LN. So let's do a little bit of review here. E to why is E like pi? Well, E is just a number. It's an irrational number. It's got that decimal that just never ends and never repeats, and you can never turn it into an actual fraction. So, we need it in lots of formulas that you haven't seen yet, but you will see them, and they're gonna come at you, and there's gonna be a whole lot of them. So let's get used to this idea of E. We need pi in formulas regarding circles and spheres and surface areas of spheres and all the perimeters and all that circumferences. So let's think about E in that way as well. Just doing a little review. E is this button right here. E to the oops. Delete that. We got not control. Just press the E button. It's so important. It gets its own button on the Inspire. That's how important it is. E to the first is 2.71828, and it just keeps on going. But my calculator rounds. So if you wanted to, you could also do E to the third power. Enter. You get about 20.086, and then of course, it gets rounded, and then it doesn't. You don't even really. That's like E times itself 3 times, but you don't even need to have a real solid idea of what the exponent could be. Like this could just be negative 0.23, and you turn that into a very small decimal and round it. Anything to the 0 power is just going to be 1, and of course, remember that you can also add. If you're multiplying bases, you can add exponents. This would be e to the first plus 9 times e to the ninth times e to the negative third. So 1 plus 9 plus negative 3 is positive 7. And if you wanted to, you could also find out what e to the seventh is. E to the seventh just looks like this. Boom. I also wanted to review just a little bit that what logs look like. Remember 4 times log 16 minus log of 256. Well, the subtraction here on the outside turns into division on the inside, and the multiplication on the outside turns into an exponent on the inside. And so we've got log base 10 of 16 to the fourth over 256, which you can actually simplify this right here. Like if you didn't have a calculator, then you could take 16 to the fourth and turn it into base 2. These are all base 2, and it would turn into a very small, much smaller number, which I'm not going to do here. Anyway, this exponent would be 3/5 because it's x to the third, and then the radical is 5 that goes in the denominator. So if it's x to the 3/5, that's the same thing as 3/5 times log base of x. So an exponent on the inside turns into multiplication on the outside. All right, here's what's new. Log base e. Oh, yeah, log of base e. What does that even mean? It don't matter. We're just going to use it. Log base e. That means the base is e, and the exponent is 3. The base is e, the exponent is 7. It can be written as ln, which stands for natural logarithm. You'd be like, hold on. There's nothing natural about e. I'm sorry, Berg. There is no way that I'm going to call this a natural thing. Well, I got news for you. By the time you finish calculus, you'll be like, whoa, I'm so thankful that we have E, because it just makes my life so much easier. All these formulas that use E, all these properties, all this work I got to do, E makes my life so much easier. Well, you're in Algebra 2 right now, so I got to say that it's hard for me to say to you, like, your life is going to be a lot easier the more we use E, but at this point it will be. We'll have some formulas very soon. And LN stands for natural logarithm because the first dude who came up with this idea was, I believe he was French. So in France, in the French language, you say you say the noun first and then you put the adjective afterwards, very much like in Latin or in Spanish. So he would have said not natural logarithm, but a logarithm natural. That's why it's ln. And that's why you got this button right here. See this fun little button? ln. You can take the natural logarithm, or the log base e of any number. So log base, it's the same thing as log, and then you actually type in an e right here to the first power of 5. These two ideas are exactly the same. You can see their decimals are equivalent. The log base e of 5 is the natural log of 5. So that's where it is on a calculator, and that's what it looks like. So let's convert the exponential form to a logarithmic notation. So we're going back and forth here. This is a logarithmic equation, and the unwritten base is e because it's we see this ln symbol. Base is e, the exponent is 1.5, and the power is x. There should be a decimal there. Great. And then you can see here, if the base is e and the exponent is x and the power is 50, then the exponent goes all by itself here and the base is e. You could write technically log base e of 50, but it's just a lot more commonplace to use ln. I mean, in calculus, you're going to find yourself writing more ln than log base 10. In physics and in chemistry and in engineering, log base 10 is usually the most it's the most often used base. However, in calculus, the most often used base is not base 10, but instead base e, so often that we have our own 2-letter abbreviation for it. It's ln of 50 is equal to x. So let's get used to it. Base e is ln. Base e is ln. Base is here. The exponent is all by itself, 3x, and so the power is 45. The natural log of x is equal to 5.8. The exponent is all by itself. The base is e, and so therefore the power is x over here. Here, base e, natural log, exponent is negative 5x. It goes by itself, and there it is. Now, in all of these cases, if you were solving for x, you can see now x is all by itself, and you'd be able to you have things that you could type into a calculator to figure out what x is equal to, and so that's next up on our list. Not next. It's one of the things we're going to be able to do. Write each expression as a single logarithm. This is what it might see. You might see this kind of question on alex.com. So if we're going to change this into a sum or difference of logs, then you can see here subtraction on the outside turns into division on the inside. The multiplication on the outside turns into exponent. So the natural log of 3 to the third divided by 9 is what this is. And if you needed to, you could also simplify on the inside using your normal exponents and just using normal arithmetic, PEMDAS kind of stuff. So here, subtraction on the outside turns into division on the inside, and this is multiplication on the outside turns into an exponent on the inside. We've seen something like this before. The bases here are all e, so we're going to use the natural log. And we've done these kinds of things before in base 10. Now we're just doing them in base e, which is natural log. Here, addition on the outside turns into, it turns into multiplication on the inside, right? Right, Berg? Yeah, it does. Okay, good. So then you get 2 times natural log of x plus 2 natural log of 4. Both of these 2's turn into exponents on the inside because they're multiplication on the outside. And the addition turns into multiplication. And then you can go in the opposite direction as well. You can take one log and split it up into the logarithm of simple inputs. Here, this is log, it's division on the inside turns into subtraction on the outside. And radicals on the inside and exponents on the inside turns into multiplication, turns into an exponent on the inside, and the exponent would be 3/5, turns into multiplication on the outside. That's what that looks like. We've done all of these things before. We've only just done them in log base 10 or other log bases, but now we're doing them in base e. Solve each equation and round to the nearest hundredth. So here we're going to solve for x, and the technique we're going to use eventually is change an exponential equation to a logarithmic equation. We can't do that unless the exponent is all by itself. So first thing we have to do is move all these other numbers to the other side. We have to undo the subtraction. We have to undo the multiplication. And now that we have e to the x is equal just a single number, now we can rewrite it as a natural log. So natural log of 6, we can just press the control natural log of 6, and we get our answer. We get 1.79176, and there it is, rounded to the nearest hundredth. E raised to the 3x is equal to 30. We're going to convert this, as we did up here, convert it between an exponential equation into a logarithmic equation. Natural log of, this is the log base e, or natural log of 30 is equal to 3x, because the exponent is all by itself, the base is e, and the power is 30. And then, in order to solve for x, we can divide both sides by 3. When you type this kind of a thing in, you can take the natural log of 30, and then outside of the log, you divide it by 3, and you get this. Notice that on you'll note that as terrible as the Mac iOS or Mac OS calculator app is, it does have a logarithmic or natural log button. So the natural log button is there. And on the alex.com calculator, it's also there as well. So that's good news. Natural log of x minus 6 is equal to 1. So here, what I'm going to do is I'm going to change it back into an exponential equation in order to isolate x, in order to get x by itself. It's basically like undoing the natural log. So the exponent is by itself, the base is e, and the power is x minus 6. And then you add 6 to both sides, and this is what you get. Same thing here. The base is e, the exponent is 3, and the power is x plus 2. And this is what it turns into. You can calculate it. So here's the big idea. Everything we did with log in base 10, you can also do with natural log in base e. Berg, it's not natural. Why? Why? It looks so weird. And to have a base of a decimal, it might make your life more complicated now, but I guarantee you, let's get used to it as best we can. Let's just turn it into something that we're familiar with, and then by the time you get to calculus in 12th grade, you'll thank me for it, because it'll make your life there way more easy. And of course, these are the things we can do. We can convert between exponential equations and logarithmic equations. We can combine them or split them up. We can solve for them. These are all things we did with log base 10. Now we're just going to do them with log base e. Temperature. Newton's law of cooling. Sir Isaac Newton touched so many aspects of physics and calculus and mathematics, and he has his own law of cooling. So it relates the temperature of an object over time in relation to the initial temperature of the object and the temperature of its surroundings. What? That just kind of means, like, if you have a bowl of soup in a room that is colder than the actual bowl of soup, then you need Newton's law of cooling to figure out exactly what it looks like for it to cool down. Anytime something is cooling down, we're going to use this formula right here. The temperature in degrees Fahrenheit of a bowl of soup over time is modeled by the function big T of little t. So big T is temperature, little t is time. And TA is the ambient temperature, where T0 is the temperature of the soup. When it's taken off, that's like at time 0, where the temperature of the soup is, and TA is the ambient temperature of the room. So, like, if you've got a 200 degree bowl of soup and it's only 70 degrees here, 200 minus 70, and it's 70 over here. Evaluate the function. So find the temperature of the soup that is initially 200 degrees Fahrenheit in a room that is 72 degrees after 30 minutes. So T0 is 200 degrees Fahrenheit. Ambient T is 72 degrees in the room. And what is the time? It's 30 minutes. And we're going to use this formula where T is in minutes here. So T30 is equal to, I don't know, that's what we're trying to find. If we're trying to input 30, then we're finding what the output would be. So T of 30 is equal to 72, that's the ambient temperature of the room, plus the difference in the soup versus the ambient temperature here, 200 minus 72, times e to the, this constant is based on, where did the 0.032 come from? It comes from soup, basically. It comes from physical, chemical properties of soup and how quickly it cools, and the bowl and all that. And then the 30 is just from the time. You can type all this into a calculator and get your answer. That's 121 degrees after 30 minutes. It cools down, after 30 minutes, it'll cool down to 121. And maybe at that point, you might be able to eat it. 30 minutes? I don't want to wait 30 minutes for my soup. Part B. Evaluate the function for t. So let's say, suppose a restaurant manager who wants to make sure that the soup is at least 180 degrees Fahrenheit when it is served to customers. So we know what it comes out at. It comes out of the pot on the stove at 200 degrees Fahrenheit, and we know that the temperature is at 72. The only thing we don't know is how much time you got to serve that soup. How much time when the soup is taken off the heat source should the server serve the soup. So this is a restaurant trying to figure out how long you've got before the food is not at the quality level you want. You know the initial temperature of the soup, it's 200. You know the ambient temperature is 72. And you know the final temperature is 180. What we don't know is time. How many minutes do you have? So you have 180 is equal to, and you can find everything in here except what this little t is, little t time. 72 is ambient, 200 minus 70. It's the same as before. 200 from the heat source on the stove to 72. And then you've got this times e raised to the exponent. So now what we have to do is we have to undo all these operations in order to eventually get at t. And so you can subtract 72 from both sides to get this, and doing the PEMDAS first was subtracting 128 degrees times e raised to this. And then dividing both sides by 128, you get 0.84375 is equal to e raised to this number. And at this point, we're going to change this from an exponential equation to a logarithmic equation. The base is e, so we're going to use natural log. And the exponent is all by itself negative 0.3032 t. The power is this 0.84375. And now you can type it into a calculator. I'll show you what it looks like, and I want you to do the same because I want you to uncover that red dot. So ready, we got the natural log button, control e to the x gives you natural log, and then 0.84375. You type along with me. We got that divide by, and then negative 0.032. And then you can hit enter, and you tell me what you get over here. And you can round it to the nearest tenth. So how many minutes you got? 5 point something. And I want you to tell me what it is. Here. We got some data here. Gaming. The table shows the percentage of people in the U.S. who play games on their mobile phones in the years since 2010. So use a graphing calculator to analyze the data. And here's some data, and the years since 2010 is like this, and then the percent is population. If we are somehow given the indication that this is a logarithmic by nature kind of design, what we can do is you can take this data, just like if this were a project. This is what the sand project looked like, and this is what other projects are going to look like, and this is what your final exam is going to look like too. You're going to have all this data, and if you are given a clear indication that this is logarithmic in nature, what you can do is you can type it into Desmos. Let's see if I got this. Yeah, it's right here. So you can make a table like this, and you can graph the points, and then you can type in the parent function of the log equation, and yeah, it's going to be in base e because of the central importance of e in exponential growth and logarithmic growth kind of applications. So you can see there's a potential for on the inside a horizontal dilation, on the outside a vertical dilation, and on the outside a vertical shift. And so what we can do is we can put all that here, and this is what we get. And so if you needed to, you can now answer questions about like what will happen in the future. So, for example, here it says use a graphing calculator to analyze the data, and if you wanted to know what year 11 was or year 12 was, or when it is exactly we get up to 100%, these are things you can now actually look at. So here, 50 years later, we're at 92%, which is kind of high. I wonder what the current year is. If you put, years, how many years are we now since 2010? And so you can put that in and find out. Finance. Janie's bank pays a 2.8 annual interest compounded continuously on savings account. She invested $2,000 in the account, and using the formula A equals PERT, determine how long it will take for her initial deposit to double in value. Assume that she makes no additional deposits and no withdrawals, and round your answer to the nearest quarter of a year. So here's what we know. We know that the rate is 2.8%. We know we're using the formula PERT. We know the initial is 2,000 and it's going to double. That means it's going to be 4,000. And what we don't know is the time. And so now that we've kind of analyzed the knowns and unknowns, we can see here 4,000 equals 2,000. And if you divide both sides by 2,000, you get 2. This 2 actually represents the double in value. So if you wanted to, you could jump straight to this kind of a formula here, this A over P. A divided by P is 2 because we're looking to see how long it's going to double. And so if you wanted to, you could just say it's 2 equals E raised to this. The 2.8 gets turned into a decimal of 0.028 and times t. Now here we've got a base of E, so it's going to turn into a log of 2, a natural log. And so the natural log of 2 is equal to 0.028t. Dividing by the decimal, and you get natural log of 2 divided by 0.028, and that gives you approximately 4.25 years, rounding to the nearest quarter of a year. I just want to take this opportunity to say at this moment that my favorite kids book to read to my kids is Green Eggs and Ham. And I'm not sure if you have any kids. Maybe you do, maybe you don't. But I want you to tell me, maybe when you get to class, tell me about your favorite kids book that you enjoyed reading. Were you a Green Eggs and Ham kind of a fan? Did you like Dr. Seuss? Or did you have something else in mind? Anyway, take care. Thanks for sticking with me, and I'll see you in class.